So when it comes to an active high pass filter design, this is how the configuration looks like. So now the capacitor is an input capacitor. It's on the input side and it is in series with Ri, unlike in the active low pass filter where it was in parallel with RF on the feedback side. That makes an input impedance Zi being obtained on the input side and RF on the feedback side. So the gain is still minus RF over Ri, but now it won't be Ri in this case because now there's a capacitor that adds an impedance, so it's going to be minus RF over Ze. At the same time, how do we calculate Zi? Zi is made up of a capacitor in series with a resistor. As you learn from electrical engineering 2, the capacitor will create some reactance XCI, which is 1 over 2 pi FCI, depending on the F being the frequency of V in. And then you get Zi to be, because they're in series, to be Ri plus XCIJ as a complex number. But the Zi we refer to in the formula of the closed loop gain there on top is the magnitude of this, which will be nothing but square root of Ri squared plus XCI squared. So that leads to the closed loop gain, voltage gain, to be equal to minus RF over Zi, which is, here I'm referring to Zi as magnitude, of course, and then that what gives the closed loop gain. In terms of decibel, it's going to be 20 log of the ratio, which is 20 times log of RF. And here we're talking about the magnitude, not the negative value, because we can't have a log of a negative value. Square root of RF squared plus XCI squared. Right. That's how we get the closed loop gain in the case of a high pass filter. But what is a high pass filter? Just to go back to what we've said already, a high pass filter in terms of frequency, it cuts low frequencies and passes frequencies above a certain cutoff frequency. But how do we work out that cutoff frequency? That cutoff frequency that defines the limits of from above which the frequencies are passed and below which the frequencies are cut off is obtained as 1 over 2 pi Ri Ci. So it's made up of Ri and Ci this time instead of RF and CF as it was the case in the case of low pass filter configuration we had before. Okay, a couple of examples to go through again and ask questions if any before we go to the next application of operational amplifiers, which is the use of an operational amplifier as a comparator. How can we use an operational amplifier as a comparator? Amplifier as a comparator. To use an operational amplifier as a comparator, we need to understand what's a comparator. The same way we define the filter, a summer, a differential amplifier in the applications. What is an analog comparator in this case? Do not confuse this with the digital comparator that you learn in digital systems. This is a comparator that compares analog values. The other one was comparing digital values. Okay, and I hope you know the difference between analog and digital values. But what is a comparator? It is a circuit that compares the signal voltage on one input with a reference voltage on the other. So if you've got an amplifier like that, if you apply a certain voltage here V1 and a different voltage V2, this time you're making sure they are different, then the operational amplifier obviously will compare Vi on the positive side with respect to V2 and being connected with VCC and ground, the output will be set accordingly. It's going to be either equal to VCC or to ground, depending on how the two inputs compare. That's how a comparator works. Okay. We will just look into this now. So the comparator basically compares one of the two input is called the reference voltage, and the other one is the input voltage. Why is this important? Because that directly speaks to its actual applications. Most of times use a comparator. Let's say you have a circuit and you're trying to monitor voltage level. Let's say you're charging a battery, and a DC battery, and you want that whenever the battery is charged above maybe 13 volt, the charging circuit must stop. So you would use a comparator. Your reference voltage will be a fixed 13 volt that you can generate with any type of circuitry, maybe 12 volt. You can generate that will be your reference voltage, and you connect that to the one side of the amplifier. You can generate that by voltage divider, for instance. From a VCC maybe of 15 volt, you can generate a 12 by voltage divider by choosing properly the two resistors. And now here will be the actual input voltage, or the actual battery. That will be the actual battery voltage. That will be all the time compared therefore to this reference voltage. And how will you detect that on the output side? That will depend on how big that is with respect to a reference voltage. So when you speak about a comparator, you normally have to speak about some form of reference voltage. Okay. So an operational amplifier, when connected, when the two inputs of it are connected to two different voltages, you notice that there will be no feedback resistor involved when using an operational amplifier as an operational amplifier as a comparator. That's why the two input voltages can be different, because the role of the feedback resistor is basically to make sure that the two inputs are kept at the same voltage, right, level. But since there's no voltage, there's no feedback resistor, then the two input voltages to the amplifier can be different. Okay. So now the fact that there's no feedback resistor, the operational amplifier is running therefore at a gain equal to the open loop gain. So it's gonna be open loop gain. That will be the gain of the amplifier. And as we know, amplifiers are designed with often a very high open loop gain. So now, very high open loop gain. The inverting input of the operational amplifier will be connected to a reference voltage, and the non-inverting could be connected to the input voltage. Either way, but the one of the input to be used as a reference voltage and the other one is a input voltage. So reference voltage meaning it's fixed. It's something you configure with a voltage divider, for instance, and it's fixed to a certain value. And the other one, which is the input, can be varying. Okay, so now what the operational amplifier will do then is, because the gain is too high, that means the output voltage will be equal to the supply, will be limited by will be maximum first of all, and will be limited by the supply voltage. So the output voltage maximum on the positive side will be VCC as explained minus V saturation, and the minimum value will be VCC. It's not ground necessarily there. It could be VEE, which is a negative value. So it will be VEE plus VSAT. Right. So those will be the two limits, because the gain is very high. So the output will be expected to be limited to those two. But now, which one will it be? V out max or V out minimum? That solely depends on how the two input voltages compare to each other. And that's what we brings the role of a comparator. So when the voltage at the positive input is greater than the voltage at the negative input, then the output voltage will just be limited to the maximum output voltage, which is VCC minus VSAT. And when the the voltage at the negative input is the one that is higher than the one at the positive input, it's going to be the other way around. The output voltage you're going to get there will be V out minimum, which will be VEE plus VSAT, VE being a negative value. So that what leads to the following diagram if you have to represent how the output of a comparator behaves. So if you have a plus VCC connected there, it's a positive value, and you've got minus VEE, if you can call it like that. VEE and negative numbers, rather. Let's stick to the same thing. Then you've got plus and negative, and you've got the reference voltage connected there. Let's say 5 volt DC, 5 volt, and you've got an input voltage there. The output voltage obtained here, and this amplifier has got a saturation voltage VSAT. So the output voltage obtained will swing between minus meaning VE being a negative number plus VSAT, and a maximum positive value of VCC. That will be V out basically with respect to V in. VCC minus VSAT. Right, so VCC just reduced by VSAT. And it will be equal to that whenever, if that's the reference voltage. So when V in is higher, in this range here, as you can see, V in is higher than Vref. V in being connected to the positive side is higher than Vref, which is connected to the negative side of the amplifier. I'm referring to those. Then the output is equal to the higher side of the higher cut of the supply, VCC minus VSAT. And in this range here, that when V in, which is equal to V plus, is less this time than Vref, which is the negative side of the amplifier. That's where we get the lower side, right? Output to be equal to the lower value. Okay, so that it's about an amplifier, operational amplifier being used as a comparator. Let's now look at an application of a op-amp. Application of an op-amp that we call the Schmitt trigger. Schmitt trigger. What is a Schmitt trigger? Because the operational amplifier comparator is sensitive, and I'll explain what that means, the output may switch back and forth erratically between plus VSAT and minus VSAT. Okay, so the VSAT here, capital V, they're referring to here in the textbook, is what I call VCC minus VSAT, or VEE as a negative number plus VSAT. Okay, just to be clear on that. So the sensitivity of an operational amplifier simply means a little, when used as a comparator, simply means that a little noise on top of the one signal could make the whole thing swing. So let's say you have a case where the input here is 5 volt V plus, and the reference is also, let's say it's 4.5 volt. So with a little noise on top of this signal, it could basculate and goes to 5.1. So the output could suddenly swing, because naturally when it's 5 and 4.5, V plus is higher than V minus, so the output is on the VCC side. So it V out goes to what they are calling VSAT in the book, which is normally VCC minus V saturation of the amplifier. When it's 5 higher than 4.5, that's what it happens. The sensitivity comes in is that in the fact that the reference could vary. Maybe resistances, remember they've got tolerances, or due to temperature change or any form of noise in around the signal, could move the 4.5 DC, could be superimposed by some noise signal that could push it maybe to 5.1. Automatically when it just reaches 5.1, meaning slightly higher than 5, output will swing from that much to lower quickly. So you get that effect, and that's where the Schmitt trigger comes in. When V in is near the reference voltage Vref, meaning almost the same as the case I chose here, 5 volt and 4.5, they could be it becomes very sensitive to noise. Noise could basculate or change suddenly the output of the comparator from high voltage to low voltage, okay, from output maximum to output minimum, such as noise. So to eliminate that erratic operation, that way the Schmidt trigger is a special type of comparator circuit comes in. And how do we design therefore a Schmidt trigger? And then we're going to learn how it ends up eliminating the impact of an unwanted or noise signal by shifting everything or making the operation of the comparator unpredictable. So to design a Schmidt trigger, we still have on the reference signal side, we'll normally tie it up to a reference value with R1 and R2, which is dependent on the output, meaning by having some feedback configured with it. So then we've got V reference to be fixed all the time. It's always the output times R1 over R1 plus R2 by voltage divider, of course, in this network, as you can see. Then the input voltage is applied there. With that being said, the reference voltage will be equal to that. It will always be compared to V in. Sorry, this is on the positive side. And this should not be confused with a Schmidt trigger, should not be confused. Of course, plus VCC is there, which is a positive value, and VEE, which is a negative value. This shouldn't be confused with a non-inverting amplifier, because with non-inverting amplifier, the minus will normally be here and the positive there. So that's the difference between Schmidt trigger and a non-inverting amplifier. So with that, the Schmidt trigger will eliminate that sensitivity. How so? Because of its feedback configuration. In other terms, the input tracks what is going on at the output. So somehow the output is dependent on the input behavior, and that maintains some level of reliability. There's some level of cooperation between the output and the input. But how does that technically happen? So we have a feedback resistor R2 and the input resistor R1 connected to set up the reference voltage. Then we've got the feedback fraction, which is obviously R1 in this case, over R1 plus R2. Then we have what we call the upper threshold point. The upper threshold point, UTP as we call it, upper threshold point is plus the feedback fraction multiplied by VSAT, and the we've got what we call lower threshold point, which on the other side is minus BA VSAT. Remember, when I say VSAT here, I'm basically referring to VCC added with subtracted by V saturation of the amplifier, or VEE added with the V saturation of the amplifier. Okay, so it's VCC plus VCC minus small VSAT, or minus VCC, but almost equal to, can be sometimes approximated to VCC on one side and minus VEE, or VEE as a negative number on the other side. Okay, with those two thresholds defined, then those two thresholds defined, the output of the Schmidt trigger will remain in its present state, meaning it won't easily fluctuate as long as the applied voltage is beyond the UTP on one end and below the LTP on the other end. Okay, so when you are inside that the zone between LTP and UTP, then you've got some uncertainty coming into play there. Okay, so that makes the original diagram that we had in terms of V out, in terms of V in, to become as follows. You now have something like that, and you have Nothing like that. So there is a level of range of V in with respect to a reference. Here we are assuming that the reference is on 0, of course, but this can be shifted to another different V reference voltage. But when the reference voltage is on 0, then you've got UTP and LTP like that, and you've got a guaranteed, therefore you've got a guaranteed negative output when you are above UTP, and you've got a guaranteed positive output when you are below LTP, right? Okay, we're gonna carry on from here by studying the difference voltage between the upper and the lower threshold, meaning the difference between UTP and LTP, and that what is normally called the hysteresis. Hysteresis voltage of a Schmidt trigger, VH, which is UTP minus LTP, which is beta plus beta, of course, VSAT minus beta a VSAT saturation, and that is nothing but 2 beta VSAT. Minus will give plus. Okay. That concludes the concept of a Schmidt trigger. And sometimes a lot of times actually, we ask you for the Schmidt trigger transfer characteristic curve. State curve, we can ask you to draw this. We can ask you to calculate UTP and LTP. We can ask you to calculate the hysteresis voltage. We can ask you to design a Schmidt trigger, etc. We can ask you to calculate the feedback fraction. Okay. The next type of amplifier application, which is not in the textbook Group's Basic Electronics, that we're gonna study in our next lesson, will be what we call the integrator circuit, as well as the differentiator circuit. I'm just pointing this out so that you can already look on it. We're gonna design an integrator circuit and differentiator circuit. As their name says, the one performs integration on a signal, on an input voltage, and the other does differentiation on an input signal. Right. Practical applications, just to revise the mathematics behind it before we study it, is that when it comes to integration of a signal, let's say that signal, the integral of that signal, it refers to, with respect to time, of course, refers to the area under the curve that you've learned in mathematics. So what the output, the total area under this curve will correspond to the output of that integrated circuit that we'll design with an operational amplifier. Differentiation on the other side, you know the concept of differentiation, but mathematically, but we're gonna come back to that. Okay, till we meet next time, I want you to please go through this. I'll upload some more tutorial questions that you're gonna go through, and please ask questions to my email address for anything you don't understand, or to my WhatsApp number. You can reach me there. Thank you.